So for this section, I've made a pretty picture, which is exactly like the first pretty picture that you see on your homework, but I thought it was a little bit easier to see this way. And what we are dealing with is the inverse trig functions. So what this is asking for is it says y equals the arctangent of x, okay? And what we, first of all, notation, this says arctangent. You could also write this as the inverse tangent that way, which is the way that you see it on your calculator. Or I have a habit, whether it's bad or not, I don't know, of writing atan of x. Okay, so what this means is this. Normally with a trig function, and I'm going to be lazy with this, we have a trig function that we evaluate at an angle and it produces a ratio. Okay, so we take a trig function evaluated at an angle will give us some ratio that we have. Well, the inverse of that means we undo everything. So the arc trig function of a ratio will tell you the angle measure at which that ratio occurs. And the issue is, and you may have to kind of sort of backtrack on your own, go back into pre-cal world and figure out why we have to restrict the domain the way that we do. But that being said is we have specific intervals that we can work within. So what this is asking is the arctangent of negative root 3. In other words, where does tangent have a ratio of negative root 3? And for tangent, you're only allowed to work on the right side of the unit circle, which is going to be quadrants 1 and 4. But you can only drop down into quadrant 4. So you can't go around through 2 and 3. You have to use negative angle measures. So this angle measure is going to be a negative pi over 3. Okay. So in other words, where does tangent have a ratio of negative root 3? That's going to happen at a negative pi over 3. This one says the arctangent of this ratio occurs at negative pi over 6. So in other words, what's the tangent of negative pi over 6? It is negative root 3 over 3. So there's a negative in front of there. And then this one will say, what is the ratio of tangent at pi over 4? And so again, you're shoving in this angle measure right here. This ratio to give me this angle measure. So what is the arctangent of x that will yield a pi over 4? Or what is the tangent of pi over 4? Tangent of pi over 4 is 1. So remember with all of these that you're working backwards, and this is going to be your little friend right here. And you may have to go out to Khan Academy or something like that to refresh yourself on why you're working with the restricted domain, because I just don't have time to get videos up for that. So normally I would give you a quick refresher in class, but no time. All right, so number 2 says, evaluate the expression without using a calculator. So I have the arc cosine of 1. In other words, where does cosine have a ratio of 1? So a while ago I said that tangent, if that's your unit circle, tangent can come up to pi over 2 or drop down to negative pi over 2. For cosine, you can start at 0 and go over to pi. So you're allowed to be in quadrants 1 and 2. So within quadrants 1 and 2, where does cosine have a ratio of positive 1? And so what is that answer going to be? Your ratio for cosine being a positive 1. Hang on one second. Okay, I paused it and I said, hang on, but anyway, you didn't know that I left. So here I am. All right, so I've got the arc cosine of 1. So remember that this is a ratio. Where does cosine have a ratio of 1? That's going to occur at 0. So in other words, the cosine of 0 is 1. Okay, so you're just undoing this stuff. So what about arc cotangent? So the arc cotangent of negative root 3. So the arc cotangent of negative root 3, again, for the cotangent, you're going to end up in quadrants 1 and 2 again. So where does cotangent have a ratio of a negative root 3? And that is going to be in quadrants. You're either in quadrant 1 or 2, so this is going to be in quadrant 2. And then where does cotangent have a ratio of a negative root 3? And that's going to be at 5 pi over 6. So at 5 pi over 6, cotangent's ratio is negative root 3. All right, so we just keep doing this a little bit back and forth. So the next one says the arc cosine of 0.013. Okay, so if we're going to do it on the calculator, first of all, it says in radians, so make sure your calculator's in radians. So hit mode. Okay, so mode, and then scroll down, make sure it says radians. I'm in degrees right now. And then kill that off. And now it says, what is the arc cosine? So hit second cosine, and it will give you the arc cosine. See it? Okay, and then you just say 0.013. So this is the ratio. That's 13 10,000ths, or 1,000ths. Sorry, good heavens. That's 13 1,000ths. So what angle measure will produce that ratio? And that's an angle measure of 1.56. So 1.56 radians will give you this ratio. All right, so we got a couple more in here. And now we're going to build some triangles. Okay, so why do we have to build triangles? We built triangles in pre-cal for a bit, and then when you go into Cal 2, you're going to find out that we cannot do some calculus the way it is in algebra world, so we convert it into trig world, do it there, and then convert back. So it's just going to help us if we make a triangle. So basically what this is saying is, given that y equals the arc cosine of x, okay, where your theta is between 0 and pi over 2, or your y, they use y, sorry I said theta. Basically you're in quadrant 1, and that's just ensuring that everything stays positive, okay? So it says, write the expression in an algebraic form. I would like to know what the cosine of y is. Okay, so they told me that I've got this thing right here. So I've got y, here's a x, and here's a 1. Okay, so the arc cosine of x, and remember this is a ratio, so over 1, occurs at y. Well, then the question is, okay, fine, what's the cosine of y? So if this is your angle measure, what's its cosine? Well, its cosine is adjacent over hypotenuse, which means the cosine of y is x. Okay, so all we're doing is undoing. So I didn't have to complete my triangle on this one, but I will on the next one. All right, so it's the same triangle. So I'm just going to write it again. So I've got an angle measure of y, and this is x, and this is 1. And it says, would you please, using the same restrictions I just had, tell me what the cotangent of y is. Okay, so I would like to know what is the cotangent of y. Well, cotangent is adjacent over opposite. So for adjacent over opposite, what am I going to do with this mess? So for adjacent over opposite, I'm going to have to complete this. So your fastest way until you get the hang of it is going to be using a different variable. So I've already got x in place, so don't use him. I've got y, don't use him. So let's just say z. So I'm going to use Pythagorean theorem, and I'm going to solve for z. So that gives me an x squared plus a z squared equals a 1 squared. And now get z by itself. So I'm going to subtract x squared from both sides. Okay, and then take a square root. And this is where this restriction comes into play right here. I was told I was in quadrant 1. So normally at this point you would take a positive root and a negative root. I'm taking a positive root because I'm in quadrant 1. So z is the exact same thing as 1 minus x squared under a radical. So instead of this, I've got a 1 minus x squared, which means now you know what the cotangent is, because the cotangent is opposite, or sorry, good heavens, is adjacent over opposite. So that cotangent is x over 1 minus x squared. Okay, so it looks like a mess, and I understand that, but if you'll notice, we're going to take something ugly in algebra world, and all of a sudden it's pretty easily done in trig world, because this may be really ugly, nasty, but then look at this, I can integrate cosine. I can differentiate, or cotangent, good heavens. I can integrate that kind of stuff. So that's what you're working towards. Anyway, let's do another one. All right, so this says, I've got the tangent of the arc cosine of root 2 over 2. So tangent of the arc cosine of root 2 over 2. Okay, so what does this mean? What this means is, first of all, that should be tickling your brain. That is a benchmark ratio. So if you've got a benchmark ratio, you do not have to build a triangle. Okay, so basically what this is saying is I have a ratio for cosine that results in a root 2 over 2. So what angle measure with cosine will give me that ratio? Well, that angle measure is pi over 4. So that entire interior part becomes a pi over 4. And now it says, well, hey, now that you know that part, what's the tangent of pi over 4? Well, the tangent of pi over 4 is 1. Okay, so that's what you're doing. You're just working inside out. The next one says, what is the cosine of the arc sine of 5 over 13? And that one is not a benchmark ratio, which means you need to build a triangle. So what is the ratio for sine? It is opposite over hypotenuse. So I'm going to build a triangle. Okay, here's my theta. I know the opposite is 5. I know the hypotenuse is 13. Hypotenuse is 13. I need the cosine of this thing, which means I'm missing adjacent. So if you use Pythagorean theorem, you're going to find out that 5 squared plus, and I used y, even though it's x, okay, just forgive me, equals 169. So you're going to find out this missing measure is 12. Okay, so now you have figured out the angle measure that will produce that ratio. I don't care what the angle measure is because I already know what the cosine of it is. So the cosine of that angle measure is 12 over 13. Okay, so now let's do another couple. So what we have is the cosine of the arc sine of 4x. Okay, of 4x. And I wrote it kind of weird on purpose because that's going to be an over 1. And so again, this is not a benchmark ratio, so build a triangle. So here's your theta. Sine has a ratio of opposite over hypotenuse. So now can you find the cosine? So I need to finish this out. And so let's just say he's z. So that means z squared equals, this side squared is not 4x squared. It is 16x squared. Equals 1 squared is 1. So I'm going to subtract 16x squared from both sides and then take a square root. So this side that I'm missing is a 1 minus 16x squared. Okay, so do I know what the cosine is? It's adjacent over hypotenuse. So the cosine is going to be 1 minus 16x squared under a radical. All right, so the next one says I've got the tangent of the arc secant of x over 3. Sorry, my handwriting's getting messier. I'm trying to hurry so I don't have to have 2 videos. All right, so I've got the tangent of the arc secant of x over 3. All right, so do I know what the ratio for secant is? The ratio for secant is the reciprocal of cosine, which means this is not adjacent over hypotenuse. This is hypotenuse over adjacent. So I have hypotenuse adjacent. And so if I want to solve for the missing side, because I need to know opposite over adjacent, that's going to give me 9 plus y squared is x squared. And I need to get y by itself. So y equals x squared minus 9. And then take a square root. So this is x squared minus 9. Now I know this part. What's the tangent? The tangent is root x squared minus 9 over 3. All right, so the last 2 problems, we're going to pull this stuff directly off of your handy-dandy cheat sheet. So, and I'm going to take derivatives of both, and I'm going to try and get it done in 1 minute. All right, so I need to find the derivative of arc secant. So if I look down here, here's arc secant. How do I take his derivative? So I take the derivative of the argument over the absolute value of the argument times the square root of the argument squared minus 1. Okay? So if I'm going to deal with arc secant of 5x, okay, what I do is I take the derivative of the argument, which is 5, over the absolute value of the argument, which is absolute value 5x, times the square root of the square of the argument. So 5x times 5x is 25x squared minus 1. That's your derivative. Okay, it's ugly, but that's your derivative. All right, so the last one is we got to do product rule, and we're not going to have time. So we'll do first times the derivative of the second, and honestly, I'm going to pick this one up on the next video, just because we're going to go straight into integration. Hang on, where's my mouse?